Hello and welcome to Lesson 38, Logarithmic Differentiation. This is the last topic in Unit 3. So what's the goal for today? I want you to recognize situations where logarithmic differentiation would be good, and then obviously I want you to be able to apply the process correctly. So those are the two things. Identify when it should be done or used, and then apply it correctly. So the short answer is you can use logarithmic differentiation at any point in time. The question is, when is the right time? When is it more efficient for you? When we look at the first two functions here, most people are going to say this should be done with quotient rule, and the answer is probably yes, it's going to be quicker. I'm going to do it with logarithmic just to show you that. The second one, though, it's quotient rule, but that top function has a product in it, so you're going to be doing the product rule inside the quotient. So that's where it may become more evident why we would want to do logarithmic differentiation. So, for the first one, I'm going to show all steps. First thing we're going to do is going to take the logarithm on both sides. I'm going to take the natural log, so ln y, and I'm going to change function notation back to y notation. It's just easier to write. Ln, and here's the argument, x minus 3 cubed, x to the fourth plus 2, all inside the logarithmic argument. We can now use properties of logarithms to rewrite the right side. We have a quotient inside a log, so we can rewrite it as ln x minus 3 cubed minus the ln of x to the fourth plus 2. So we've just taken quotient rule out of the picture. And keep in mind or remember that the exponent in a logarithm becomes a coefficient. Now, when I do the next couple of examples, I actually skip that second step and I go right to this step. I just want to show it in the first note, one thing at a time for you, and then you're all set to go. So now I'm going to take the derivative on both sides. So 1 over the argument, derivative of the argument, 3 times 1 over the argument multiplied by the derivative of the argument, 1 over the argument multiplied by derivative of the argument. And now I'm going to multiply, because what I want to get y prime by itself. I want to find the derivative. So in this step, I'm going to multiply both sides by y. So times y times y. So that would mean that y prime will equal y multiplied by 3 over x minus 3 minus 4x cubed over x to the fourth plus 2. And in the end, I'm going to tell you I'm going to skip this step as well because y is just equal to the original function. So really, I'm just going to replace y in my final step with that statement at the top there. So in the end, the derivative of that function above is going to be x minus 3 cubed over x to the fourth plus 2 multiplied by 3 over x minus 3 minus 4x cubed over x to the fourth plus 2. So is it quicker than doing product law, or quotient rule, sorry? The answer is probably not for this one. What it does is it reduces, you don't have to worry about chain rule. So there are a couple of advantages. It comes out in a more factored form, a little bit nicer form. It's the next one that's probably a little bit more efficient. And I'm going to start skipping steps and kind of do this in what I call real time. So right away I'm going to take the logarithm of both sides. So I have 5x plus 2 squared on top, x minus 1, x minus 3 to the fifth. So now I'm going to write, using my rules of logarithms, to write this out in the expanded form. And I'm going to put that coefficient out right off the get-go. Plus the log of x minus 1 minus, because that last term is in the denominator, oops, and I forgot to put the 5 out front, because it will become a coefficient. So with logarithmic differentiation, really there's no worry about doing a chain rule because all the exponents become coefficients. Now I'm all set to take a derivative. 1 over y prime, equals 2 times 1 over the argument multiplied by derivative of argument plus 1 over argument multiplied by derivative of argument minus 1 over the argument, derivative of argument. Now, I'm going to do a couple things here at the same time. I'm going to multiply both sides by y to get y prime by itself, and that y I'm going to replace with the original function, because that's what it is. It's equal to the original function. So it ends up looking like this. Y prime equals the original function, x minus 1, all divided by x minus 3 to the 5th, multiplied by 2 times 5 is 10 over 5x plus 2 plus 1 over x minus 1 minus 5 over x minus 3. So there is the derivative of function g. Okay? It will look quite different if you do the product and quotient, or the quotient rule with the product rule embedded inside, but I will tell you the algebra comes out looking neater with this method. All right, both methods are going to be equally correct. I'm not going to say ever to you should have used quotient here or logarithmic there. I will mark whatever you give me. So here's a product rule that involves a bunch of chain rule. So I just want a comparison for you here. So again, we're going to take the log of both sides. And again, I'm going to do this in real time. So I'm going to do the acceptable skipped steps. So ln y equals 2 ln of the 4x squared minus 3 plus 3 ln of the x squared plus 3. Now I'm just going to take the derivative. 1 over y prime is equal to 1 over the argument multiplied by the derivative of the argument plus 1 over the argument and multiplied by the derivative of the argument. All right, so I'm going to clean this up. Same thing, I'm going to multiply both sides by y, but I'm going to do the substitution of the original function. So y prime would equal 4x squared minus 3 squared, x squared plus 3 cubed, multiplied by, now I'll have 16x over 4x squared minus 3 plus 6x over x squared plus 3. And there we are. So, again, you will get full marks regardless which way you do it, as long as you do it correctly, obviously. I'm just providing you with an alternative method that may have more appeal. Now the second example, or the fourth example I should say, this one lends itself much more to using logarithmic differentiation, because if I take the log of both sides here right off the start, the exponent, again, becomes a coefficient. So we end up with an expression that looks like this. So now we really have product rule on both sides, and it's a more simple product rule than maybe we would have been dealing with above. So just applying our product rule here, we end up with an expression that looks like this. Derivative of the first one would be 1 y prime ln x plus y 1 over x multiplied by 1. Just cleaning it up. xy prime over y prime ln x plus y over x. Going to move all the terms with y prime to the left side. And anything that has no y prime moves to the right. Common factor out my y prime. And final step, divide both sides so that it's isolated. X over y minus ln x. And there you go. There is the derivative, the slope, at any point along that function. All right. Final example. Again, if you use the derivative rule for exponential functions, you'll come out with the correct answer. So I'm not saying don't use it. Also, there's a squared missing here for some reason. So if you could put 2x squared in there, and maybe draw it in a little bit better than I did. I'm going to do it with logarithmic method. Do you have to? Definitely not. And in this case, it's probably the same either way in terms of how hard it is algebra-wise. So remember that exponent becomes a coefficient. So 2x squared minus x comes out front. Ln 3. Now that ln 3, that's just a number. It's just a coefficient. So we really only have to take the derivative of that expression there. So when we do take the derivative, 1 over y prime, we'll end up with 4x minus 1 in brackets ln 3. Multiplying both sides by y and replacing at the same time 3 to the exponent 2x squared minus x multiplied by 4x minus 1 multiplied by ln 3 is what we end up with. Okay? It's the exact same as what you would have ended up with probably in one step if you're using the rules for derivatives of exponential. All right, so I'm not telling you that exponential is the way to go. I am telling you that logarithmic is another method out there, and it has its time and place. So doing the substitution, I want to find the slope at 1/2, so I'm going back to function notation. 2 to the exponent 1/2 squared minus 1/2. 4 times 1/2 minus 1 ln 3. Cleaning this up, the exponent, 1/2 squared is 1/4, times 2 is 1/2, so the exponent's going to be 0. 2 minus 1 is 1, ln 3. So that goes to 1. That is a 1. So the slope is ln 3 at that coordinate. It's almost like I planned it that way for a teacher example. Absolutely crazy. Okay, so finding the line of the tangent line, the equation for the tangent line, we go back to what we learned in grade 9. We do our substitution, x minus 1/2 plus 3, and there we are. That is your equation for your tangent line. All right, and that's obviously going to be what the application questions are on this upcoming test, as that seems to be every example that was repeated. So there's the assigned homework. If you have any questions, please make sure you seek me out. The review is posted, so it's all set to go. And good luck with the Unit 3 test.